and Osaka University, Japan. His transition from a postdoctoral fellow to an assistant professor and finally as a scientist at CSIR NIST showcased a dedication to cutting-edge research and international collaboration. His work has earned him prestigious recognition, including the Ramanujan Fellowship and Kerala State Young Scientist Award and Raman Research Fellowship. With a prolific publication record over 50 papers, Dr. Vijaykumar stands a leader in his field. His current research spans fascinating and highly relevant areas. Today, we are privileged to learn from his vast experience and insight. His expertise, particularly in novel materials, will undoubtedly enrich our understanding and inspire new research direction among us. Please join me in giving a rousing virtual welcome to Dr. Vijay Kumar. We eagerly look forward to his section. Thank you, sir.
Am I audible?
Yes, sir. Please.
Can you see the slide?
Yes, sir.
Okay.
Yes,
So
sir.
thank you, Miss Adina, for the kind words of introduction. And today I will be talking about the topic halide perovskites-based materials for advanced optoelectronic devices. Okay. So this is a relatively new class of materials. New means in science, even 10, 15 years are we consider new. Actually, it came to limelight only by 2012, 13 in that time. So it is almost 12, 13 years already over, but still we consider it is relatively new. And a lot of research is happening in the area or in the materials in this area, especially for various optical and electronic device application. So the major application of this material is in solar cells. That is how it came into limelight, because it can give a photo conversion efficiency close to 25%, which is similar to the first generation solar cell, that is the silicon solar cell. But the price wise or the ease of fabrication is far superior for this material compared to the silicon based material. That is how the class of material halide perovskites came into limelight. But later people found that this is not only suitable for the solar device application, but also for various other optoelectronic device application. I will name those applications in the coming slides. So I believe that it is important for the faculties to understand, get an idea in the area of halide perovskites. And also I would like to introduce what kind of activities I am doing and my research group at the CSR NIST is doing. So just a second. Yeah. So before going to the details of the material, I would like to first show what are the major applications. As I mentioned, solar cell is one of the major or most important application of this material. And the second one is light emitting diodes. So if you know about these class of devices, solar cells and light emitting diodes, these are actually having two different requirements, almost opposite requirement. For example, in solar cell, the material is absorbing light and the charge carriers are generated. Charge carriers means hole and electrons. So the charge carriers will be generated and the charge carriers will be traveling to opposite electrode, and we are collecting the charge carriers at the electrode, and it will complete the circuit and giving the current. Okay, but in the case of light emitting diodes, it is just opposite. We are actually injecting electron in hole to the material, and that will go to the medium, that is the functional medium, and there the hole and electron will recombine and that will result light emission. So it is just opposite, where in the solar cell light is absorbed and the charge carriers are generated and we are collecting them. On the other hand, light emitting diodes, we are injecting the charge carriers and they are combined and form light. Okay, so normally most of the material, if it is suitable for solar cell, it may not be suitable for the light emitting diodes, and if it is suitable for LEDs, it is not suitable for solar cell. But in the case of halide perovskite, you can actually tune the properties of this material in a way that you can get both these properties. Okay, in one form of the material it is light emitting, and in the other form it is solar cell device application. But not only these solar cells and the light emitting diodes, it can be used for thermoelectrics. Thermoelectric is nothing but where we are actually using the temperature difference to produce a voltage difference and finally extracting the current. So if you have a surface which is having like a 50 degrees Celsius or 100 degrees Celsius, and it is exposed to the ambient temperature. So you have a temperature difference. The surface of the material is at 50 or 100 degrees Celsius, and the ambient temperature is, for example, 30 degrees Celsius. And because of this temperature difference, actually you can convert that temperature difference into voltage. That kind of phenomenon and that kind of devices are called thermoelectric devices, and this material can be used for thermoelectric application also. Similarly, another class of application is piezoelectricity. Piezoelectricity, when you apply forces, okay, or you are pressing it, or compression or applying pressure, you are generating current. That is called piezoelectric current. Similarly, it can be used for ferroelectric application, like it is having the dipole moments organized, and that can be used for generating energy. And artificial synapses, that is called memory devices. Okay, so memory devices, we know in the computer, normal computer device, it is like 0 and 1, two levels are there, and these two levels are used for data storage application. But in brain, we know that it is not a binary system, it is having several additional layers, and it can, that is why we can think in a very complicated manner. And this binary devices reached a saturation, and for the future application, especially with the artificial intelligence is widespread nowadays, and for these applications you need much higher or complex systems which can used for storing the data, and which is capable of processing the data. And that should be something similar to the neural network of our body or the brain. So these materials can be used for that kind of application. So these are some of the major application of this material. In addition to that, it can be used for photocatalysis, like carbon dioxide reduction, hydrogen evolution, organic synthesis, and it can be used for sensor applications like temperature, pressure, moisture, explosive detection, and photo detectors. It can detect a certain wavelength of light, and that I will explain in my slides, because I am actively working on photo detectors. And it can be used for field effect transistors, lasers, batteries, capacitors, hydrogen storage, X-ray imaging, etc., etc. So you name any optoelectronic device, this material can be used in one form or other. Okay, only the difference is that you have to chemically change the structure of the material, like from the three-dimensional material to 2D material to 1D material. And in some cases, for example, capacitor kind of devices, you may need to go to zero-dimensional material. Okay, that a chemist can easily do by changing the anion or cation or the component in this material. Okay, so that is why a chemist, I am basically a chemist can do a lot of work in the area of halide perovskite materials, and we can tune this material for any specific application like named in this slide. So what are the properties of this material, why this is very become so popular, and why it is suitable for applications we mentioned in the previous slide? Okay, I will mention some of the advantages or some of the properties of this material. One is the high quantum yield of luminescence, and from this you can get an idea that it is like a light emitting diode application. You need the quantum yield. Quantum yield is the ratio of the energy you gave and the ratio of the light or the energy in photons you emitted. Okay, So if it is very close to 1, it is the best. And if it is like below 50% or 40%, it is not suitable for many light emitting applications. So normally this perovskite material shows very high quantum yield, not only the luminescence quantum yield, but also the electroluminescent quantum yield. Most of the devices, it is electroluminescence, not the photoluminescence. So in both cases, electro and photoluminescence, it shows very good efficiency. It is very close to 100% of efficiency in many cases. So that is one reason. And second one is low cost fabrication. So you can make this material at the laboratory with a minimum chemistry environment. You can make these materials, and that can be used for the device application. So unlike silicon based system, there you need a very complicated fabrication facilities and the expensive fabrication facility, high temperature fabrication facility. But in this case, you are using low cost fabrication facilities. Okay, you can do solution phase synthesis, and you can do the normal film fabrication techniques, and that actually reduce the cost of the devices. Okay, already many perovskite materials are found suitable for the commercial application, especially in the solar cell devices. But in other devices, the commercialization is still yet to happen. That is why it is still in the R&D stage. Like we are working on the R&D, research and development stage. And another property is high optical contrast is suitable for the imaging purposes, biological imaging kind of applications. And you can tune the excitons. There is the exciton can be tunable to any wavelength. Like if you want some application in the UV region, and in some cases in the visible region, and some cases in the NIR region, you can easily tune the exciton to that particular region by simply changing the structure of the material. And you can generate excitons at the room temperature. Electron and hole can be generated at room temperature. You don't require high temperature for working this material in the optoelectronic devices. For example, some of the ceramic materials, it has to be heated at like 500 degrees Celsius or 600 degrees Celsius to use it as the sensor device. Okay, but in this case, this material can be used at room temperature. You don't need any high temperature for using this material for the device application. In addition to that, it shows excellent light absorption coefficient, like dyes. Okay, organic dyes, they can absorb a very good quantity of light, and that can be used for the dye sensitized solar cell. But perovskite can show one order higher absorbance. For example, if the organic dye like ruthenium dye or something is showing 10 to the power of 5 exciton means absorption coefficient, these materials show like 10 to the power of 6 or above for the same purpose or the same property. And the charge carriers are usually having very long. Their lifetime is very long, so it can easily reach the electrodes without any recombination. And the diffusion length also very long, like a micron diffusion length. So these charge carriers can easily travel from the light hitting side to the electrodes, or the vice versa, from the electrodes to the functional medium. And as I mentioned, the excitons can be tuned. Similarly, the band gap can be tuned. For example, for the solar cell application, you may need a band gap of 1.5 electron volt, and that you can easily tune by incorporating tin or lead, or by changing the organic component of the material. Okay, I will discuss the structure in the coming slides. And you can also tune the exciton binding energy by changing the quantum confinement properties. You can easily tune the binding energy, and you can narrow the emission wavelengths if you require a narrow band gap, or if you require a broad band gap. Suppose for a photodetector, you may require narrow band gap, but in some cases you need broadband detection. In that case, you can tune the band gap, and as well as the emission wavelength from the narrow to the broad wavelength. And also it shows remarkable defect tolerance. For example, there are many quantum dots or the nano crystals based on chalcogenide materials, and these chalcogenide materials are not defect tolerant. If there is some impurities present in the material, its properties will deteriorate. Okay, so in this case, that decrease in the property or the functionality is not happening because the defect tolerance of these materials are very high. One reason is that defect bands are very close to the valence band and the conduction band of this material, and that actually since it is very close to the valence band or the conduction band, there is no difference in the properties. Similarly, there are so many other important aspect of which is useful for this material for using it for the device application. So to get a better understanding of the material, we will first try to understand the structure of this material. Basically, it is having a very simple structure that is called the AbO3 structure. In this AbO3 structure, the B cation, okay, both A and B are metal cations. Normally, the A is a monovalent cation like calcium plus, potassium plus, or sodium plus, and B is normally a dication or trication, mostly lead or tin or titanium, germanium, bismuth, etc. And AbO3O is the oxide anion. So these three components are there: A cation, B cation, and oxide anion. And B cation is actually covered with 6 oxide anion and forming an octahedral structure. So that is the basic structure of a perovskite material. And several of these octahedral structures are combined together to form a 3-dimensional structure. And by forming the 3D structure, there is a void is formed, and these voids are filled with the A cation. So that is needed for the structural stability as well as for the charge stability. Okay, because it will compensate the excess negative ions on the octahedral structure, because there are many oxygen ion and it cannot be compensated with that. Negative charge is not compensated with the B cation alone. So you need something else, some positive cations to compensate the charge of these oxide anions, and that is done with the A cation. So this is the structure. Initially the B cation that is situated in the middle of the octahedral structure, and this A cation, the oxide anions are forming the octahedral structure, and several of these octahedron is combined together to form a 3D structure. And when the 3D structure is formed, there will be interstitial voids, and these voids are filled with A cations. Okay, and you can embed different cations in the A site as well as in the B site, and depending upon the which cation you are using, you will get an impressive array of properties. You can tune the electrical properties, you can tune the mechanical properties, magnetic properties. So you can get an array of properties, and you can basically engineer the material depending upon your applications, from the light emitting or the magnetoresistance or capacitance or photocatalysis application. You can tune the properties based on your requirement. You just need to change the A cation or B cation. Later, people started working on this material in the laboratory. Actually, these AbO3 materials are mostly found naturally, like in Ural Mountains in Russia. These are inorganic perovskites or the perovskite oxides. They are actually naturally occurring, and the similar structures people started working on with X anion. Instead of oxide anion, they started using halide anions, okay, iodide or chloride or bromide, and they found that it become much more easier to make this material. Actually, this AbO3 material, they are not so easy. They are actually very strong, and you need high temperature to work on those material to make it to some other form, or to make films or some other crystals or something. You need to break it, and or if you want to synthesize at laboratory, you need to use like 500 degrees Celsius or 700 degrees Celsius ovens, and that is not a easy process, and that will obviously increase the cost of fabrication. So people started working on this structure because this structure is very interesting to work on, because you can change the anion or cation and you can get an array of properties. So instead of oxygen, people started using halide anions, and they found that these, especially these iodide, chloride, and bromide, they are very suitable for this kind of structure of, except fluoride. They are very small in structure, and they are they cannot give very stable perovskite structure. So they started working on AbX3 instead of AbO3. They started working on AbX3. The only difference is in the last component, that is, instead of oxygen, it is halide anion. And mostly people are started using organic cations instead of inorganic cations. They started using organic cations like methyl ammonium, formamidinium cations. These are very small cations, small organic cations. And of course, you can use inorganic cations also, and they can you can produce all inorganic perovskite. If you are using organic cation like methyl ammonium or formamidinium, you will end up with a hybrid perovskite. That is the organic inorganic halide perovskite, that, or it can be called hybrid perovskites. Okay, and one of the most popular hybrid perovskite is the methyl ammonium lead iodide. That is giving something like 25-26% efficiency in solar cell. The structure is again the same as the AbO3 structure. Here the B cation occupy the middle of the octahedron, and the octahedron is formed by 6 halide anions, and several of these octahedrons are joined together to form a three-dimensional structure, and the voids formed by this octahedral 3D structure is occupied by the A cation. So either this A cation is the methyl ammonium or formamidinium, like a small organic cation. If you are using big organic cation, that will split the layers. This layer and this layer will be split by the bigger organic cation, and that will lead to 2D structures that I will show you in the coming slide. And basically, this halide perovskite, that is organic, inorganic halide perovskite, is considered as the golden boy of the next generation solar cell, light emitting diodes, sensors, and photo detectors, and other devices I mentioned in the previous slide. Because here there is a lucky combination of the unique optical and electronic properties together with the cost-effective processing. Okay, so basically the optical and electronic properties are coming from the inorganic clusters. Okay, these octahedral clusters are basically inorganic structures, and inorganic structures are normally give very high optical and electronic properties compared to organic compounds. But at the same time, organic compounds are having very easy processability, facile processability, and flexibility. Organic materials are, on the other hand, they are brittle and they are not flexible. They are hard material, and their processability is very, very poor. So this is a lucky combination. Actually, the optical and electron properties are governed by the inorganic clusters. On the other hand, the processability part is governed by the organic components. If it was opposite, for example, if the optical and electronic properties are coming from the organic part, and the processability component, processability properties are coming from the inorganic part, then it is the worst combination. Okay, but it was a lucky combination. It is giving the superior properties of the both components. Okay, the optical and electronic properties from the inorganic part, and the processing from the organic component. And it was mostly studied by this gentleman, Professor David B. Mitzi. He was, and he is still working in Duke University, USA. Actually, he brought this material into limelight, and most of his studies was done in 1995. Actually, the first comprehensive study was done by Professor H.L. Wells in 1890s. Okay, that was like more than a century ago. But that time, nobody was interested in this material. Nobody understood this is a highly promising material, and people overlooked the importance of this material. But in 1995, Mitzi published one science paper, and he did most of the studies or the basic understanding at that time. But still, it didn't come to the real limelight even in 1995. It actually come to limelight in 2010 only, when people started using this material for solar cell application by Korean group Park in Korea, and also Great Cell. Great Cell was working. Michael Great Cell was working with the DSSC, and the DSSC, dye sensitized solar cell, reached a saturation of performance. So he decided to think about something else. Instead of the organic dye, he started using the perovskite dye as the active component, and he found that it is giving very good efficiency. So he moved into the perovskite solar cell from DSSC, and many groups along with Park and Great Cell, many groups all over the world started working in this area. And from 2010 onwards, you can see an explosion in the number of papers. Okay, at that time it was like below 100, and then by after 2-3 years, it became 1,000 and 2,000, 3,000 numbers were started coming, and now the numbers are pretty high, because this material, as I mentioned in the beginning, are suitable for a large number of applications, large number of optoelectronic application, and there are a lot can be done by the chemist. We can do a lot of do synthetic manipulation and synthetic engineering in this material to get suitable properties, and the physicists can work on the device engineering part. The different layers can be used to extract the best efficiency from the solar cell devices, and engineers can actually convert these small scale devices into a large level modules, and or something which is really suitable for the commercial applications. So the chemist, physicist, and engineers can do a lot, and in the interdisciplinary way, and that actually created a perovskite explosion in the last several years. So if you just Google halide perovskite, you can get a lot of papers in this area, and even Mercedes-Benz, they have some plan to use this material as a coating over their car, and that can be used to convert the solar cell into electricity, and that electricity would be enough to run the car. A small or small to medium size SUV can be run with enough light absorbed from the available sunlight, and that would be enough to run the car. That is their plan. Of course, it is in the conceptual level, and it is not commercialized, of course. But that is the level of research happening in the area of halide perovskite. So now I will discuss what a chemist can be done in this area, because I'm a chemist and I am doing the synthesis part, and I am trying to, my group is trying to make different structures of perovskite. Of course, a chemist can do a lot of things, because it is having different dimensions. Okay, it can be made in 3-dimensional, it can be done in 2-dimensional, it can be in 1-dimensional or 0-dimensional. Okay, the basic difference is that in the case of 3D structures, all the octahedral units are connected at the corners. So the corners are shared and form a 3D structure. Several of these octahedrals are arranged, packed in a beautiful manner, and these structures forming a robust 3D network. So in all direction, X direction, Y direction, Z direction, these octahedral structures are joined. So if there is a charge carrier is formed, or exciton is formed, exciton, it is nothing but the electron and hole combined together through a Coulomb electrostatic interaction, Coulombic interaction. Okay, so the pair, electron hole pair, is called an exciton. So when an exciton is formed by light absorption, okay, that is a fundamental material property. When chromophore material, which are capable of interacting with light, they can absorb a photon of energy from the light, and that photon can excite the electron from the valence band to the conduction band. Then a hole will be formed in the valence band, and electron will be placed in the conduction band, and that electron hole pair is called the exciton. Okay, that exciton can travel in any direction in a 3D perovskite. Okay, it can travel in the X direction, it can travel in the Y direction, and it can travel in the Z direction or the Z direction. Oh, so it is like a very smooth expressway and and it can very quickly travel from one direction to other direction without any hindrance. Okay, and this is the ideal scenario for a solar cell device. Okay, the light is absorbed and exciton is formed, and exciton can easily move. And if there is a bias voltage, normally in a solar cell we will apply a bias voltage, so the exciton will dissociate into electron and hole, and that will go to the respective electrodes. Okay, and it will complete the circuit and you can extract power. Okay, so this is the 3D structure. But if you increase the size of the organic cation, so earlier I discussed it is we are using simple small organic structures like methyl ammonium or formamidinium. If you use slightly bigger, like a benzene with a NH3 plus, okay, it is slightly bigger. In that case, these layers will get separated because the bulky organic group will go into the structure, and that will uh, push the inorganic layer. These octahedral structures are inorganic layers, and these structures will be, or the layers will be pushed apart to form a 2D structure. Okay, the layer is forming a two-dimensional mat-like structure, and this is a 2D structure. And here the exciton can go only in two directions, X or Y direction. Okay, along the Z direction, there will not be any possibility. It is like a quantum well structure. Okay, it is restricted only in two direction. Okay, so that is 2D structure, and we can still play around with the organic cation. You can use slightly bigger or slightly branched kind of structure. In that case, again, it will force the inorganic cations or the inorganic building block to pack only in one direction. Instead of 3D or 2D, the octahedrons pack only in one direction, and it will be further confine the exciton into one direction. Okay, so there is a quantum confinement effect will start playing, but still the exciton can travel along the material to X direction, left or right, but not to the Y direction or not to the Z direction. Okay, so this is a one-dimensional material, and the last one is zero-dimensional material. If you use slightly bigger or slightly different organic cation, you will end up with isolated octahedral structures. Okay, like this. Isolated octahedral structures. Still, it is a perovskite structure, but the octahedrons doesn't have any interaction. They don't have any electronic interaction or other electronic communication between them. Okay, so if an exciton is formed in one octahedron, it will remind there that exciton will be highly bound. The energy of interaction between the excitons will be very, very strong. This is a real quantum confinement effect. These excitons are confined into the octahedral structure. They cannot travel. So what they will do, they will recombine. Okay, easily recombine, and that will result as a light emission. Okay, so if you want something like a emitting material, light emitting material, so instead of going for 3D, it is better to go for the lower dimension, particularly zero-dimensional perovskite. Okay, but if your application is something solar cell kind of application, it is better to go for the higher dimensions like 2D or 3D material. And in that case, the exciton can easily travel to the electrodes and easily get dissociated at the electrodes, and that can easily give current. Okay, so depending upon the requirement, our device application, a chemist can design material in such a way that it can be resulting a 3D structure or 2D structure or 1D or 0D structure. Okay, so it is like a simple, like a cooking. You are changing the ingredients and you are getting a totally different product with a different taste and texture. It is like that. So how you can make this material for the device application? Of course, in solution. Most of the application you cannot do in solution. So you need to convert it into a material form. Okay. So here you can make either in the film state or in the large single crystal or microcrystal form or even nanocrystals and quantum dots. Okay. So these are the major. Of course, in some cases, solution is also okay. for like some typical sensor kind of application, even solution is okay. But if you want to make a solar cell or a light emitting diode or a photo detector, you need to make most cases films. Okay, for making films, you can go for a sequential deposition technique. So you have one component deposited, like the inorganic precursor. Okay, if it is like a lead, it is lead iodide or lead bromide, you can deposit, and then you can methyl ammonium iodide, you can drop cast or the, you can deposit. So together they will react and form the perovskite structure. Okay, so that is a sequential deposition. One reagent, and over that the second reagent, and you will get the material. Okay, because the entire thing will react on the surface of the substrate. Other one is the one-step deposition. You mix the ingredients like the lead iodide or the methyl ammonia iodide. You mix in solution in a conical flask, and you take that entire mixture and deposit onto a surface. Okay, that is another method for making films. Okay, and in some cases, we go for the large single crystals or micro crystals. Okay. For example, photo detector kind of application, it is better to have some crystals in some cases. Okay. And in many cases, sensor application or uh, even like detection of X-ray, that kind of application, the crystals are better. So you can make crystals of this material that are so very easily, like a simple anti-solvent vapor-assisted crystallization. You dissolve the material, all the reagent in one solvent, and you add another solvent in the vicinity. Okay, so the vapor of this solvent, that should be an anti-solvent. That means the compound should not dissociate in that solvent. Material should not dissociate in that solvent. So it is an anti-solvent. So this anti-solvent vapor will go inside the mixture, and that will force the material to crystallize. That is one method. And another one is the inverse temperature crystallization. You heat the material at like 100 degrees Celsius or 120 degrees Celsius, then you cool down slowly. So once it is reaching a lower temperature, normally these materials will start crystallizing. Okay. And similarly, you can make nanocrystals or even quantum dots. Okay. So when it comes to nanocrystals, the size should be below 100 nanometer. Quantum dots are normally below like a 10 nanometer size. Okay. These microcrystals and single crystals normally in the micron to milli to centimeter scale. Okay. Even like 1 or 2 centimeter size crystal also can be made. For the nanocrystal synthesis, we use the ligand assisted reprecipitation, that is commonly used for the chalcogenide based nanocrystals like cadmium selenide, cadmium sulfide kind of system, or hot injection. You heat the reaction mixture and quickly add the one reagent to the reaction mixture, and suddenly the nanocrystals will start forming, and you can precipitate it and take out and centrifuge and get the nanocrystals and quantum dots. Okay, and these are the nanocrystals that made, and these are the absorption and emission properties. So from the picture, you can see that emission can be tuned to any wavelength. So you can see the blue color, kind of violet tinge blue color to perfect blue color, and then cyan color, and to green color, to yellow, to orange, to red, to deep red. So we are covering the entire visible region. We can even go to the UV region and to the NIR region on both either sides of the electromagnetic spectrum by simply changing the X part. X means it can be either chloride, or it can be bromide, or it can be iodide. For example, if we are using X is equal to chloride, all three anions are chloride. In that case, we will get a absorption like this. Okay, it is slightly below 400 nanometer, and emission is slightly above 400 nanometer. Okay, it is purely blue to violet color. And when you start replacing the chloride with the bromides, okay, you are replacing here, it is all chloride, and in the next stage, you have two chloride and one bromide. You will slightly shift the spectrum to here. Then you have like one chloride, two bromide. Further, you can shift to slightly into the red region. And again, you reduce the number of chloride and move to more and more uh, bromide. If it is like all bromide, okay, methyl ammonium bromide, Br3, then you will get a beautiful green color like this. And then you further move to iodide part. Okay. In that case, you are replacing the bromide with the iodide. Then it will start moving to yellowish, then to orange and red and deep red. And you can further, in all iodide case, you will get like a NIR spectrum. Here you can see it is above 700 nanometer. It is coming close to the 800 nanometer. That is the NIR window. So it can easily go to the NIR region by simply changing the halide ion from chloride to bromide to iodide. You can easily change the absorption. That is, absorption is shown here, and the emission properties, and it can be visually detected from the violetish blue to deep red color. Okay, so this is one way, and similarly you can get different structures like a cubic structure, octahedral structures, nanorods, and flake-like structures, or like bundled flakes like this, small flakes or bigger flakes like this. So you can have all kinds of flexibility. You can change the structure, you can change the morphology of the material. In all cases, you can tune the optical and electronic properties, and that is required for the device application. For optoelectronic application, you should have the flexibility to tune the optical and electronic properties the way you want. That is what we showed in this slide, and these are some of the papers we published in the nanocrystal work in the area of nanocrystals from 2014 to this year. You can go through some of these papers if you want to get a better idea about our work. But if you look at the literature, there are thousands of papers coming in the perovskite nanocrystal. There are amazing works are going on, and you can get a better idea if you just do a search on halide perovskite based nanocrystals. And we showed this material can be used for several applications like photosynthesis, natural photosynthesis kind of application. It can be used as a light absorbing medium. You can see this light absorption is coming in the visible spectrum. That is what the natural photosynthetic systems also doing. They are absorbing in the visible spectrum and converting that into to some chemical energy. So similarly, we can actually absorb the light, and it can be given to some other compounds like rhodamine B, rhodamine 101, and Nile red kind of molecule. And that we established, and we published these papers in Advanced Optical Materials, the JPC, Chemistry Asian Journal, etc. So here you can see the energy transfer happening in this material. So initially we were getting a very sharp emission, which is the green emission of the material. We were using the bromide-based composition. The bromide-based composition is normally give beautiful green emission. And when we started adding small quantities of rhodamine 101, this is the rhodamine 101, you can see the emission in the green region, 531 nanometer is quenching, and subsequently there is an emission in the 606 nanometer. This quenching of the emission is emission coming from the nanocrystals, and this is the emission coming from the fluorophore, that is the rhodamine, that is the acceptor, energy acceptor chromophore. So finally, you are getting a beautiful emission from the rhodamine 101, even at a very, very low concentration of 0.35 micromolar. In percentage wise, it is hardly 3 or 4% of the material is enough to get like a 91% of quenching of the donor and significant emission from the acceptor. Similarly, we established you can actually do the make a composite of this perovskite in a polymer medium. In polymer medium, the stability become much more higher because we were able to prevent the cation or the ligand exchange in the nanocrystal. Normally, we are adding a ligand, a long chain ligand to the nanocrystal to stabilize it. Okay, but in a simple solution, this actually these ligands will are dynamic and they may show some kind of moving within the system. So we can avoid when we incorporate the nanocrystals in a polymer media. It is a steric hindrance is there. It is a very constrained medium. In that constrained medium, the nanocrystals are highly stable because these capping ligands cannot move from the tip of the nanocrystal to other area, and we were able to get a very strong stability, very high stability, and by incorporating a small quantity, very small quantities, even much lesser than the previous quantity of Nile red, we were able to get a beautiful white emission because the cyanish bluish cyan color is contributed by the nanocrystal, and the yellowish orange color is contributed by the Nile red. Since it is complementary, this bluish cyan and yellowish orange, they are complementary, and that can cover almost the entire visible region. We will see the emission as white. Okay, so we were established the white light emission in these materials, and similarly we established that this can be used as a electron transfer medium, not only energy transfer. We can use it for the electron transfer, not simple electron transfer. We were able to show that there is excitation energy migration. I will explain that in the coming slide what is excitation energy migration. So before that, I will just show what we did. Here in the first TEM image, you can see the nanocrystals. They are isolated nanocrystals. So in a solution, it is like an isolated nanocrystal. And into this isolated nanocrystal, we added C60, that is fullerene. And we were able to see significant congeing of the emission that you can see here. This is the initial emission, and after adding something, the emission conged, and further addition, the emission is further conged, and then it is a significant congeing by adding almost 1 milligram per ml of C60. And this is in solution, but in film, you can see the nanocrystals are very close to each other. And in this film state, once you excite at one point here, that exciton can travel to other region. Okay, in solution, it is not possible because these are isolated nanocrystals. There is no connectivity between neighboring nanocrystals. But in the film state, the nanocrystals are well connected. They are close to each other. So when you excite at one point, they can easily transport, that exciton can easily transport to the other part of the film. That is called the excitation energy migration. The exciton is migrating. Okay, that energy is migrating from one point to another point, and finally it reaches to the acceptor.
যা ব্ল্যাঙ্ক ছিল মানে গেলে তাহলে কানতে যেতাম
Yeah, so it can travel to one point to the another point within the film, and we try to understand what is basically happening and what is the photophysics behind this. Okay, so it is slightly a deeper photophysics. I will try to explain in a relatively simple manner. So in the nanocrystal solution, it is isolated nanocrystals. So when we add more and more amount of C60, it will go and attach with these nanocrystals, and that will quench the nanocrystal. So if the C60 is attached, that will completely quench the nanocrystal. But if it is not attached, okay, if some nanocrystals are free, it will emit just normally. Okay, so what you see that with the increasing concentration, you will see a decrease in the intensity, but not the this emission rate or the lifetime. Okay, so initially and finally the emission lifetime is same because whatever is emitting, it is emitting just like normal. whatever is quenched, completely quenched. But in the case of the film, it is very interesting. Though it is having a lifetime of 1.3 microsecond in the solution, in the film state, because of excitation energy migration, the exciton is traveling from one side to other side. It takes some time, and that time is getting reflected. Okay, that time delay is added up here, and the lifetime has increased from 1.3 microsecond to 4.2 microsecond. And interestingly, the nature is different. In the film, even with a very, very small quantity of C60, there is a significant decrease in the lifetime. Here, the lifetime is not decreased, only the intensity that you can see here, the fluorescence intensity only decreased. Okay, but here, not only the intensity decrease you can see here in the film, it is much more emissive and it is decreased. And not only that, the lifetime also decreased from 4.2 to 210 nanosecond, because we try to show this in a schematic representation. In the this is the normal solution state. When you excite, you are getting an emission. Okay, exciting at the blue wavelength, you are getting a green emission light. But when you added the C60, it quenches the emission. You are not getting any emission here. Okay. But in the case of film, it is organized in a very self-assembled, beautiful manner. So when you excite, the excitons are formed and it is jumping from one point to other point and finally getting emission. And that time delay is reflected in the lifetime of the fluorescence. But when a small, very, very small quantity of C60 is added, then this excitation energy migration is channeled into electron transfer, and that can be used for some other purpose, just like a biological system, biological or the natural light harvesting system. That actually the initial process is light absorption, then the second process is excitation energy migration, and third process is the electron transfer to the reaction medium, and from the reaction medium that energy is converted into chemical energy. So we reached up to the third level, okay, of a typical natural photosynthesis, that is the light absorption and energy migration and electron transfer. Okay, and we published this work in the Angewandte Chemi. This is one of the top level journal in chemistry. And some of the remaining work we published in the nanoscale after 2 years. So this is the work we carried out, or we are doing in our laboratory, that is the nanocrystal based work. And we are also working on lead free material, because most of the high performing perovskites are having lead in the structure. But as some of you may know, lead is a neurotoxic element, and it is better to avoid or minimize the use of lead. Of course, completely removing lead also a problem in many cases. For example, batteries, lead-based batteries are still we are using commercially. And only thing we need to make sure that these lead-based things are not reaching the environment. So either we need to encapsulate it properly, or after the usage of that battery or whatever device, you need to dispose it properly. Okay, the way it is established, or the scientific way you have to do the disposal. But of course, that is a different thing, and that is something related to sustainability and other aspect. Of course, we are talking chemistry here, and as a chemist, actually, we can altogether remove lead from the structure, and that is what we try to do, and what we try to understand, whether if we remove lead completely from the structure, how the structure will look like and how the properties will be, and whether you can use it for the application which is useful or which is used with the lead based material. So we try to understand this aspect, and my students done a detailed study with many of these material, and they developed several materials, and these are some of the structures we developed, and these are some of the structures we studied and analyzed and tried to understand the structure and property. So as you can see, in most cases, we are not getting the 3D structure. Okay, in the lead-based, the conventional perovskite, hybrid halide perovskite, it is a 3D structure and it is corner shaded. But in many cases, we are like getting that edge shared structure, or in some cases it is face shared structure. But of course, in some cases we are getting the corner shade structure, but still it is not a 3D structure. It is like a 1D structure. This is like a one-dimensional growth, and you have a organic part, and then again the 1D. But it's one part is like 0D. There is no connectivity, but in one part it is connected, or still you have like a edge shared with two octahedrons are connected. So there is a large possibility, or large structures are possible. Okay, so we did detailed studies, and we published our work in Chemistry Materials, Journal of Material Chemistry, chemistry material, and whatever we did up to 2021 and 2022, actually we published as a review in Accounts of Chemical Research with a cover page, and this is the cover page we designed. Here you can see the perovskite structure. We are irradiating the perovskite structure with the light, and the charge carriers are generated, and the electrons are moving through the organic component, and the holes are moving through the inorganic part. This is a simple schematic representation. Actually, the process is much more complicated. And we further conducted a lot of work, and we published something in Advanced Functional Materials, Advanced Material. These are top level journals with like impact factor close to 30. I will roughly go through some of these recent works, like what we did in 2024 and 2025 with some more details. So before going to that paper, I will show in general what we did with this lead-free perovskites. So we tried to remove lead altogether, completely from the perovskite structure, and try to understand how it is affecting the structure, how it is affecting the properties. Okay, so this is our first material we developed, that is a methyl ammonium bismuth iodide. So in the instead of lead, we used bismuth. So bismuth is actually in the 3+ state. Lead is in 2+ state, and bismuth is in 3+ state. But the 2+ lead and 3+ bismuth are isoelectronic, same electronic structure they are having. But bismuth cannot give a structure similar to lead. That is what we understood. It is actually giving a edge shared structure. The octahedrons are edge shared and forming a bioctahedral structure like this, and that is a zero-dimensional, because these bioctahedrons are not connected together. They are individuals. Okay, they are isolated. So it is giving a zero-dimensional structure, and you have electronic barriers between the octahedra. It is mainly by the organic part. So it is a quantum dot based, or quantum dot type kind of electronic dimensionality, just like a quantum dot. There is no electronic communication between the quantum dot from this part to this part, or from this part to this part. Okay, so it is having barrier on all sides. So obviously it is not so suitable for the solar cell kind of application. So we try to understand whether it is suitable for some other application. For example, it is having a large electroactive area, because you can access all the entire octahedral structure from every direction. In a 3-dimensional structure, only the surface is accessible. So here we can access this surface of the octahedra from every part, and in addition to that, these ions present in this structure, they are easily movable. Okay, unlike a 3D structure, there the ions are not easily movable. Of course, some ion migration is possible, but here it is much more easier. So we try to use it for the capacitor application. There the this ion migration can play a key role. So we developed a capacitor device like this, and we incorporated the material in a carbon sponge kind of electrode, and we impregnated with our perovskite material, and try to understand how the ion migration is affecting, and we were able to get a very beautiful capacitance which is pretty stable for several cycles. And this was the first lead-free perovskite based capacitor device application, and that we published in 2017. So basically, in the charging process, this methyl ammonium and the lead ions from the electrolyte can easily access the active perovskite material, and in the discharge form, it will go back to the perovskite structure, and it is stable also. So in the next stage, what we did that we moved to a slightly bigger organic cation. Instead of methyl ammonium iodide, that is the smallest organic cation, we moved to the propane diammonium cation, that is slightly bigger, and it is having two sides. Two sides can bind with the octahedral structure. So we made a new structure with this, and here you can see along one direction. Okay, along the c-axis, it is electronically connected. There is no hindrance of this organic component. But in the a-axis and x-axis and y-axis, this is x-axis and this is y-axis. There is a barrier made with the organic part, and along the z-axis, it is not forming a barrier. So electronically, it is active along the Z c-axis in the crystallographic axis. I'm talking about the crystallographic axis. A and B, there is hindrance, and C is there is no hindrance. So it is like a quantum well structure. Okay, you have barriers on either sides, but in one direction you don't have any barrier. It is called a quantum well structure, and this quantum well structure we exploited for the photodetector application. So along one direction, the electron can easily jump, and we try to understand how it will respond to the wavelength. So we used the UV lamp and excited or irradiated the material with the UV lamp, and this is the material. This is FTO electrodes, and we try to understand how much jumping is there. So from 100 nanoampere, we were able to get something close to 200 nanoampere with a on-off ratio of 2.1 and a relatively good responsivity of 1.14. And that is, at that time, it was good enough. Like in 2019, this 1 milliampere and an on-off ratio of 2 is good enough. But of course, during the last several years, we improved the numbers to very, very high values, which is like some of the state-of-the-art perovskite photodetectors we developed. So before going to that recent work, I will explain what we did after the second material. So when we analyzed this material, the electronic properties are inferior compared to the lead-based material. Lead-based materials are highly superior when you consider the electronic application for solar cells or light-emitting diodes. So we try to understand what is the problem here. So basically, in this low-dimensional material, what is the problem? Actually, I showed in the beginning, the charge carriers or the exciton that the electron holes are very close to each other, because that is basically within the octahedral unit. So they are very close to each other. So the interaction between the electron and hole is very, very high, and that will result high exciton binding energy. Okay, you try to understand the term exciton binding energy. Exciton means that is the electron and hole pair, and that binding and that energy of that binding is very high. Exciton binding energy is pretty high. And if the exciton binding energy is very high, the dissociation of the exciton is difficult. Okay, that is so obvious, isn't it? So the exciton binding energy is high, and the dissociation becomes very difficult. That is why we are not able to get good efficiency or good performance with this lead-free material. But on the other hand, okay, lead-based material, the exciton binding energy is low. You can easily separate the electron and hole. You can see it is already well separated, and so by simply giving a small bias voltage, you can easily separate them into electron and hole. Okay, of course, we cannot bring back lead. So what we can do with our bismuth or tin-based material? So instead of using a simple organic cation, we slightly improvised. Okay, we used phenylethyl ammonium, that is an aromatic one. So earlier we used methyl ammonium, then we used propyl diammonium, both are aliphatic. Okay, so we used a aromatic unit in this case, and these aromatic units can actually polarize. Okay, unlike the aromatic aliphatic one, this can relatively polarize, and that polarizability actually reduce the dielectric confinement. Okay, so in addition to quantum confinement, there is dielectric confinement, because there is a dielectric difference between the inorganic component and the organic component. This inorganic, the dielectric constant is high, and organic, the dielectric constant is low, because the polarizability is poor for the organic part. So one is high and one is low, and that is actually a confinement. Just like quantum confinement, here is dielectric confinement. So if you use a polarizable organic cation, you can actually reduce this difference. Okay, so you can bring the dielectric constant something closer to the inorganic structures, and that can reduce the dielectric confinement. So that is our next target. What we did, that we incorporated the phenyl ammonium, or the phenylethyl ammonium cation into the perovskite structure. Since it is a organic, the aromatic compound, it can have better polarizability. Better polarizability means the charges are there, and that charges actually give high dielectric constant. That dielectric constant will be something very close to the inorganic one, and that will reduce the dielectric confinement. Okay, if the dielectric constants are too different, dielectric confinement is higher. Here we are improving the dielectric constant, and because of that, the dielectric confinement has reduced, and that got reflected in the conductivity property, in the photoconductivity. We measured the photoconductivity of this material. And you can see in the methyl ammonium based system, the photoconductivity is low, and we were able to get like 2 to 3 times higher photoconductivity in the case of this benzyl ammonium based material. Okay, and in addition to that, we have found one aspect. We studied the film state property and found that the film growth is controlled by the organic component. Normally, in a perovskite system, the film growth is controlled by the inorganic part, that is octahedral thing. But here it is controlled by the organic part, and that is a novel observation. Okay, the organic component actually playing a key role in other cases. Till 2019, the researchers were using that methyl ammonium kind of small units. There they actually are inert component, and they don't participate in the structural aspect of the material. Okay, here we were able to bring a role for the organic component, not only the polarizability and reducing the dielectric confinement, but also it directs the structural properties of this material, because it actually pulled the growth in that packing direction. That is why we were able to get a significant peak in at 0.20 reflection. Okay, that actually corresponds to the growth of this, or the packing of the organic component. Okay, so further what we can do. Okay, so we used methyl ammonium, then this propyl diammonium, then we used a organic cation. That polarizability is very useful, and that improved the properties, photoconductivity. But that is not good enough. You need to have this organic part supporting the electronic properties. Earlier in the case, it is only structural properties. So you should have, it is supporting the electronic properties. So it should transport either electrons or the hole. So what we did, that we used a semiconducting material. Okay, so far nobody was using the semiconducting material as the organic cation, but we try to incorporate the semiconducting material into the perovskite structure and see how much it can improve the electronic properties. Okay, so this is the material we designed. We were able to get a one-dimensional structure, and this organic part beautifully stacked, forming a well-defined structure. And when we studied this material, and we were able to get a very high photoconductivity signal, because we did the studies, theoretical studies, and we found this organic component also contributing to the electronic structure of the material. Okay, that electronic structure contribution actually reflected in the photoconductivity, and we were able to get a significantly higher photoconductivity for this material. Okay, to understand, get a better idea, I will explain what kind of band gap is observed, or the electronic structure is observed in this kind of materials. It can have four different structures. One is a type 1A, another one is type 1B, third one is type 2A, fourth one is a type 2B. So if the valence band maximum and conduction band minimum. So the top one is the conduction band, and this is the bottom one is the valence band. Okay, so the valence band maximum and the conduction band minimum is contributed with organic component, then it is a type 1A material. Normally type 1A you won't get in perovskites. Normally inorganic part will define both the valence band maximum and the conduction band minimum, like this. Okay, so normally you will see a type 1B band alignment for a perovskite structure, because both the conduction band minimum and valence band maximum is contributed by the inorganic components, okay, like bismuth or lead or iodine and that kind of structures. Okay, but if the conduction band minimum is contributed by the organic component, the blue one, okay, conduction band minimum, and the valence band maximum with the inorganic one, then you have a type A structure. Okay, so organic component is giving the valence conduction band minimum. Okay, that part is decided by the organic component. And if it is reverse, like valence band maximum by the inorganic component and conduction band minimum by the organic component, then it is a type 2B. So in this structure, we got a type 2A. That means the conduction band minimum is contributed by the organic component. That means the electrons will be traveling through the organic component and holes will be traveling through the inorganic part. So that is what we designed and achieved with that material. We did, of course, we made several structures and we compared it with the literature reports, and we were able to get a band gap which is below 2 electron volt. At that time, getting below 2 electron volt for a bismuth based structure was not reported. In all cases, it was 2 or above, except this case. So we were able to easily achieve below 2 electron volt, and this electron volt 2 or 1.5 is very much suitable for the solar cell kind of applications. Of course, this is not good enough for solar cell. We used it for some other applications like photo detector application. Okay, so I will go to this photo detector application quickly. What we did in the last 2 papers, one is published in 2024 in advanced functional material, and one is in 2025 in advanced material. So this is the first one. This is a tin-based material, again a lead-free material. Why this photo detectors are important? Because they are used for the telecommunication application, medical imaging, security systems, and they are essential for spectroscopy application. Any spectroscopy systems like UV absorption emission or X-ray detectors, everywhere you need these photo detectors that has to sense the light and give a output signal in electronically. Okay, and for environmental monitoring, biomedicine, industrial application, or these sophisticated application, you need photo detectors in that device structure. So we were making the photodetectors with our material, and most of our materials were in the UV region. They are sensitive in the UV region, broadly in 200 to 400 nanometer. In some cases, they are highly sensitive in the deep UV, like 200 to 280 nanometer. And UV and deep UV is particularly important for astronomy, medical defense, environmental monitoring, air purification, secure communication, medical imaging, etc. Okay, so this is the material we designed and synthesized, and it has a robust structure like this. It is a isolated octahedral structures, but these are connected well through hydrogen bonding and through the organic component. You can see the OH, C double bond OE, NH, NH2. All these are capable of forming or hydrogen bonding, and because of that, we were getting a very robust structure, and we confirmed it is a SN4 plus structure, not SN2 plus. SN2 plus normally oxidize easily to SN4 plus and decompose the perovskite structure. So we were not willing to work with SN2 plus. We worked with SN4 plus, and this is the absorption in the powder and in the film stage. And here we did the analysis, and here the inorganic component is contributing to the valence band. I mean the conduction band minimum, and organic component contributing to the valence band maximum. That is type 2b band alignment, and we did the detailed band gap analysis and understood the mass of the hole, that is minus 4.91 ME, and effect of mass of the electron, that is 2.41. It is comparable, and both the electrons and holes contributing to higher charge carrier mobility in this system. And we studied the photoconductivity in the film state and in the crystals. In the crystal, it is showing the isotropic, the anisotropic nature. Along the parallel axis, it is giving a better signal, and along the perpendicular axis, it is less conductivity. And the films are showing much better conductivity and very high carrier lifetime of 37 microsecond in the crystal, and 57 microsecond in the film state, that is state of the art or the record at that time. And we did detailed photo detector analysis with these materials, and our material was giving very beautiful photoconductivity signal at 254 nanometer. That is a deep UV range, and with a beautiful rise and fall time. And it is giving a consistent current, and this is giving stability analysis after as prepared and after 4 weeks. And this is a responsivity and the detectivity. These are the parameters of characteristics of a photodetector device, and responsivity and photo current for an extended period of several minutes. And this is the simple structure we used, an FTO electrode, and deposited the material between the FTO electrode, and the electrons will jump to this, and holes will jump to the other part, and we are applying a small bias to drive the electron in holes. And at that time, that means the 2024, we were getting some of very close to the state of the art with 10 to the power of 11 Jones detectivity and 9 ampere per watt. Earlier in the beginning, we were getting milliampere per watt. Now we got 3 to 4 order higher, and an external quantum efficiency of 49. That is good at that time. And we broke that values in the next work, that is another work we published in Advanced Materials this year. And here we made a bismuth-based material, and this is a material. It is having a beautiful absorption up to 550 nanometer, and this is the band gap analysis we carried out for this material, and this is the photo detector analysis we did, and it is much faster It is like the rise time is almost half compared to the previous report, and fall time also lower, and it is giving best efficiency for the 365 nanometer. 254 is also equally good, but in the visible region, the efficiency is low. And here we got a on-off ratio of 7 into 10 to the power of 4. So in the initial stage, we were getting just 2, not even 10 to the power of something. It is just 2. Here it is like 7 into 10 to the power of 4, and it is working at. Hello. Hello. Okay, so we are getting the property at a ultra low dark current of 0.12 picoampere. Detectivity is very, very high. It is into the 10 to the power of 13, and responsivity also very good, and external quantum efficiency is 717. It is very high at that time. Of course, now we broke that record also. We were getting like 4,000 plus. It is actually called a phenomenon called photoconductivity gain. I am not going to that technically difficult discussions. So these are the analysis we did, the photodetectivity, and in summary, we developed several materials, several novel lead-free perovskite material, and similarly many nanocrystal material, and we did the studies like energy transfer, electron transfer, and excitation energy migration, and how we can channel that excitation energy migration to electron transfer. Similarly, we contributed a lot for the development of lead-free perovskite structure. It is very essential for the future development. The lead-based materials are amazing. They are giving very, very high efficiency, very high potential for almost all optoelectronic device application I showed in the initial slide. Of course, but we need to find, as a chemist, we need to find alternatives. Of course, the lead-free materials are not as efficient as lead-based material, but in some application, like a photodetector application, they are equally good or even surpassing the lead-based material. Okay, so there is a lot a chemist can be done in this area. Of course, for the device application, we have collaborators, and these experiments and the material development are done by my students. These are the students, and most of the contributions are given by Chinnadure. He was working in Korea as a postdoc. John, he's working as a postdoc in Switzerland. Avija, she will be going to US. She was in US for last 1 year, and she will working on a NASA project she will join in this month itself, and these are the main contributors, and other guys working in this area are like Amarjit and Akash, Nishana. These are the students, and I have collaborators for the memory devices or the neuromorphic computing, synaptic applications. I have people in Poland for the deeper photophysics and applications, like means study like femtosecond laser flash photolysis. I collaborated with a Malayali professor working in Hokkaido University, Japan, Professor Vastevan Biju. And for the theory analysis, theory studies, Sudeep Chakravarti, he's a professor at Harish Chandra Research Institute in India. For the photoconductivity analysis, I have support from Professor Saiki in Osaka University, and I have support for the device making from IST Trivandrum. Simple photodetectors we are actually making in our own laboratory. We have all the facilities for that. And I have some people in Russia in ITMO for the other optical analysis, and I thank the funding agencies, all funding agencies like DST, NRF, SCRB, and their collaborative projects, etc. And finally, I thank you all for your kind attention, and I am happy to answer a few queries if you have anything in the points I discussed in general, or in some specific queries also. I am happy to answer. Thank you all. And I also thank the organizers for this opportunity to interact with these teachers and this FTP program. Thank you all.
Thank you so much, sir. Dear participant, it's your turn. You may raise the questions or queries. You can also use the chat box for the asking questions. And also, we are sharing the feedback in chat box, so you can kindly fill it. So some of the questions are in chat box. Please.
Yeah, I can see one message in the chat box. Why are lead-free metal halide perovskites being developed? So I explained that during my presentation. I am again explaining it. Lead-based material, the major disadvantage is the toxicity of lead. Okay, it is a neurotoxic material, and it can result neurodegenerative diseases. Can result Parkinson's and Alzheimer's kind of disease when it is going to the bloodstream. Of course, lead is not going to the bloodstream, even though we are using lead for several applications. But still, it is important, at least, especially from the research and development side, it is important to replace lead with other less toxic or non-toxic material. That is why lead-free halide perovskites are being developed. So I can see one question: how do these lead-free perovskites compare performance to traditional lead-based perovskite? As I mentioned, lead-based perovskites are superior in solar cell application, but in some other application like photodetectors and neuromorphic application or the memory device application, they are equally or even better. Okay. So solar cell application, still there is a lot to do in the lead-free scenario, but in they are very good for photodetector, in some cases light-emitting diodes. Definitely in memory devices, we did a lot of memory device application. They are excellent, even better than the lead-based systems. Yeah, some people are unable to fill the feedback form. They need access. So maybe admin can do that later. And if they have any queries, I am happy to answer that later also. So the coordinators can send me the questions combined together, and I will try to send the reply. It means I can send the reply to the administrators. Okay. Thank you.
Okay, sir. On behalf of the organizing committee and all the participants of the FGP, I extend my sincere gratitude to our distinguished resource person, Dr. Vijay Kumar. Your talk has encouraged our understanding of this topic. Now, I welcome Ms. Anju for giving a thank you note. Please, Ms.
Okay, today's resource person, Vijay sir, introduced us a new material, halide perovskite based material for advanced optoelectric devices. Sir started our session with the basic concept of halide perovskites. It's a class of material with organic cations and metal halide anions interacting together primarily through electrostatic force of attraction. Initially, sir, just given a various field or applications includes photocatalysis, sensor, photodetectors, field effect transistor, laser, battery, capacitor, hydrogen storage, and X-ray imaging. It shows very excellent light absorption coefficient, long charge carrier lifetime, high diffraction length, narrow emission wavelength, tunable band gap, that is adjustable band gap. Then comes to structure. The structure of perovskite AbO3 type structure. Then moving to metal halide perovskite, instead of oxygen, halogen AbX3. Halogens such as iodide, chloride, or bromide can be used. Then he emphasized the term golden boy, this type of AbX3 as the next generation of solar cell, light emitting diode sensor, and photo detectors. Then explain the term perovskite revolution. It's due to its lucky combination of unique optical and electric properties together with the cost-effective processing. So work is focused in synthesizing 0-dimension, 1-dimension, 2-dimension, and 3D perovskites actually. Then turned to the preparation or synthesis method of haloid perovskites. He explained the various methods very well. The UV visible spectrum study, how it changes with the variation of halide ions, clearly gives the explanation. Then explain the photophysical properties of a system involving perovskite nanocrystals and C60 fullerenes acting as an electron acceptor. Sir described well how adding C60 affects light absorption, emission, and fluorescence, which is important for applications such as optoelectronics, photovoltaics, and sensing. Then low-dimensional lead-free hybrid metal halide. It's a unique work. The research work has the journal cover page in accounts of chemical research indicating its scientific significance and impact. Sir explained how band alignment occurs in layered organic inorganic perovskites. Depending on the alignment of the energy bands, layered perovskites can exhibit different electric properties, which is useful for applications such as solar cell, LED, and photo detectors. So synthesizing is lab the lead-free hybrid perovskite material N2-amino-ethyl 2-hydroxybenzene bromide. Structure consists of inorganic tin bromide octahedra connected with an organic ligand. Hydrogen bonding networks helps create a stable layered arrangement similar to a quantum well, where charge carriers are confined in the inorganic layer and guided by the organic layer. So actually, with great respect and gratitude, I take this opportunity to express our heartfelt thanks to you for the insightful and the informative session today. A good session leaves us informed, inspired, and curious for more. And today's talk has done exactly that. On behalf of everyone present, I extend our sincere thanks. Thank you, sir. Thank you very much.
Thank you.
Thank you, ma'am. Okay, dear participants, we think you are ready for the section 6. It's my distinct pleasure and honor to extend my heartfelt and warm welcome to our esteemed speaker for this online faculty program, Dr. Hemachandar. He is highly accomplished academician and researcher, currently serving as an assistant professor in Department of Electrical and Electronic Engineering at the National Institute of Technology, Pondicherry. He completed his PhD from prestigious NIT Raipur in year 2020. His dedication to teaching is evident in his prior roles, where he served as an assistant professor at Gayatri Vidya Parishad College of Engineering for Women, Visakhapatnam. His research profile is truly impressive and speaks volume about his expertise in cutting-edge technology. He has a prolific publication record, including 16 journals with 3 IEEE transactions, 25 conference and 6 book chapters. He also contributed to innovation by filing 4 patents. His core strength lies in the design and development of power electronics converters for solar and the electrical vehicle application. His key areas of interest, which align perfectly with the focus of modern power engineering, include multi-porter, DC to DC converters and their control, fast charging technique of electric vehicle battery, multi-level inverters and their control, renewable energy application, battery management system. Beyond this, his research and teaching, Dr. Hemachandran is also committed to fostering a culture innovation, currently serving as a convener of the Institution of Innovation Council at NIT Pondicherry. His research experience, particularly in the rapidly evolving fields of power electronics for EV and renewable energy, makes him an invaluable resource for this activity. We are confident, and his section will be highly insightful and beneficial to all participants. Sir, we are privileged to have you with us. The virtual floor is yours. Welcome, Dr. Hemachandra.
Good evening, all. I think I'm audible, right? Please confirm. Am I audible?
Yes, sir.
Yes, sir.
Yeah, thank you. Yeah, thank you. Thank you, ma'am. Thank you for the organizers to help. To give me this opportunity to participate in this 6 days online FDP on advanced materials, rare earth, and critical minerals. Thank you, ma'am, for such a wonderful introduction. Let me share my screen. My screen is visible, right?
Yes, sir.
Yeah, thank you. Yeah. So the topic given, or it is something like the role of lithium-ion battery technology. Just turn off my video for some time. So the role of lithium-ion in battery technology. So where are we using lithium-ion batteries? First question is, where are we using lithium-ion batteries? So you talk in terms of a mobile, which is almost, I should say, sixth finger of our hand, the mobile technology, where we use a battery. So that battery is a lithium-ion battery. Or you consider a laptop. So the battery which we use in a laptop is lithium-ion battery. So, and you take an electric vehicle, again, lithium-ion comes into picture. So wherever you look into, whatever a mobile device or a portable device you have, it is having this lithium-ion battery. No, yes, right. But why are we more interested in lithium-ion alone? So there are many other battery technologies that are available. Now, why only lithium-ion? So yeah, these are some applications where you have lithium-ion batteries. I'm not sure how many are from electrical background or electronics, mechanical background. Maybe it is a mixture of all departments. So first application, as I told, it is mobile. So wherever you see a mobile, obviously there is a battery, and that is a battery with lithium ion. Electric vehicle, again lithium ion. Now this is the other application, the third one. This is application of renewable energy system in our household purposes, or maybe for the so-called industry purposes, whatever it is. Again, it is a lithium ion battery. So why this lithium ion has come into focus, and what made it um, really more valuable? So the modern energy ecosystem hardly depends on the portable, efficient, and renewable energy storage, and that is why we have more energy storage. So where are we more concentrated on energy storage? Everywhere. Electric vehicles, you need a battery to run the vehicle. Renewable energy storage, where you need solar and wind, whatever you take, you need a battery for storing the energy during the daytime. That is what this actually this third picture depicts. So if you clearly observe the third picture, yeah, during the daytime, you just observe the battery. During the daytime, battery is getting charged when the sun is there using the solar energy, and during the night time, after the sunset, the battery is getting discharged, because during that time there is no solar, so you cannot get power. So that is what is the importance of your solar battery technology there. Similarly, we have consumer electronics, mobile, laptop, etc. Even if you see drone, which is now widely used, especially after our Operation Sindoor, where we have made some drone operation, and even we were able to destroy some drones from the other enemy countries. So there again, you have a battery. Again, that battery is lithium-ion battery. So as per a report, the total global battery demand is around 5 terawatt hour per year. 5 into 10 power, I think 12 per year. That is the battery energy demand. And that is anticipated by the year 2035. Now, why it is so anticipated? It is because electric vehicle need this, renewable energy system need this. We are having mobiles. Each year we'll, or at least in a year or two, we keep on changing the mobiles, laptops, everywhere. So the global energy demand is obviously very high. And out of that, if we look into the statistics, 85% of the market is by lithium ion. Only lithium ion batteries are widely used. Now, why do we use that? So first we'll start with lithium. What is exactly lithium? So lithium, coming to the atomic table, it is in atomic number 3, given with the symbol Li. The atomic weight is 6.94. It belongs to an alkali metal group, and that is one of the lightest solid element on Earth. And it was discovered in 1817 by Johann August Arfvedson. Now, where do we find that? So we find it in hard rock minerals like petalite and spodumene. Lithium brines like Chile, Bolivia, Argentina, they are having lithium brines over there. A lot of lithium is available. And maybe, if I'm not wrong, within the last year, it was announced by the central government, the government of India, that we have lithium reserves in Jammu and Kashmir, somewhere near Jammu and Kashmir. So that is again, one more added advantage to India. But yes, it is also available. And we also have lithium present in seawater enclaves, but of course, not of any usable quantity. So why is lithium so special? It is because the major advantage of lithium is lowest atomic mass. So the value of lithium is the lithium's value is around 6.94 grams per molecule, and because of this, it makes the battery lightweight. So, in case if you remember, when electric vehicles have just entered into the market, the range of the electric vehicle was very less, and the weight of the electric vehicle was a bit more. The reason was those days lead acid batteries were highly used in electric vehicles also. Whether knowingly or unknowingly, we still use lead acid batteries in our vehicle, not electric vehicle, normal automobile. So in case if you go with a two-wheeler, you have one battery, that is a lead acid battery. Similarly, if you go with a car, you have one battery. This battery which powers your lighting system and all the things. So those batteries are having higher weight when compared to lithium. So lithium, because of its atomic mass, it is very light in weight. And another advantage is highest electrochemical potential, which actually enables high cell voltage. So if you go with these lithium ion batteries, each cell will have around 3 to 3.6 volts per cell. So that each cell we make it into different combinations of series and parallel and make it one complete battery pack. Similarly, we also have a very small ionic radius, which is helpful for fast diffusion through the solids. And we also have another advantage, that is high specific capacity, which is 3860 milliampere hour per gram. That is, it is having very high energy density. When it comes to energy density, it is something like it can store more energy in less volume. Energy density means how much volume is required to store some energy. So very high energy, it can store in a very small volume. And it can easily form ions. It can also, it also has the property of intercalating into materials. So what actually is this electrochemical potential? This is nothing but, as we know, every element has some tendency to either lose or gain electrons. So the lithium has a reduction in, it has less potential. That means it is having an excellent reducing agent. Because of this reducing agent, it is having an advantage of high voltage reactions. So lithium, when it is lithium as it is, we take, it is having one proton and electron, Li plus and E minus. And the voltage that each cell of a lithium will have around 3 volts, minus 3.04. So cells with lithium ion can reach around 3 to 4.2. And this 3 to 4.2 is a very good number, because if you compare with its counterpart lead acid, the lead acid batteries have a voltage of somewhere around 1 to 1.5 volts. Similarly, the nickel cadmium batteries also have a very low cell voltage. So that is around again 1 to 1.5 volts. So this way, lithium has the advantage of higher voltage. So if you compare it, lithium with other battery ions, so the lithium is having a high, as I told, it is having a electrode potential of around 3 volts. The ionic radius is around 0.76, and relative mass, this has been already told, this is 6.94 grams, and significance, it is having one of the fastest ion mobility. The next category of battery ions which are now slowly entering into the market is sodium batteries. Even though the sodium batteries are coming into the market recently, they have their own advantages as well as disadvantages. The advantage is that it is even having it is even cheaper when compared to lithium ion, but the electrode potential is again less. So it is around 3 volts, it is around 2.7 volts. And ionic radius, it is 1.02, and the relative mass is a bit higher when compared to lithium ion, which is 22.99. And of course, it is cheaper and also have lower energy capacity. What I mean to say here is, suppose I am, since I am from electrical background, most of the explanation I tried to be it in electrical. So suppose I have a battery, two-wheeler battery. It is having, say, 48 volts battery. So if I call it as a 48 volt battery, we will have somewhere around, we require somewhere around 16 to 18 lithium ion cells packed in series parallel combination or series combination, and in order to provide the required AH, we require some 16 into, say, some 2, for example, 32 cells in series parallel combination. If you consider the same in sodium ion, for series combination to provide 48, 16 to 18 is not really sufficient. We need to go for some 20, around 20, around 20 to 22 we need to go with. So there we have increased the number of batteries or the cells that are actually required for the vehicle. So we need to go with beyond 20. Next, similarly, we also have one more disadvantage, which is like, even though it is having it is cheaper in rate when compared to lithium ion, the energy density of sodium is a bit low. That is, more, in order to have more energy, it requires more volume. Next is magnesium. So that is again having an electrode potential of around 2.37 volts, and again relative mass is very high, around 24.3. It also has a very high charge storing capability. Next is the hydrogen ion, which has no electrode potential but relative mass, so it is not suitable for solid electrodes. So this hydrogen ion is generally used in other applications like fuel cell and other applications. So this is what is the evolution of battery technology. It is not like first time we have seen the battery, or this gives a general how this battery technologies have evolved and when did it start. Actually, in 1817 we had the first lithium discovery by Arfvedson and Berzelius, and in 1822 lithium metal has been isolation of lithium metal has started, and first primary lithium battery was in 1962, and then in 1973 the alkali metal salt was introduced. Now slowly if you proceed further, again in 1972 there has been the first lithium primary cell, and in 1972 solid lithium ion iodine cell has been introduced, and so on. So now in 2022, if you speak about, we have the latest technologies with lithium ion, which are very which have become uh, a bit what you call cheaper, but in those days it was very costly. So first lithium ion battery was introduced in 1991 by Sony. From there on, the evolution of lithium batteries have come into picture. But initial days, maybe from 1990 to 2005, around 2000s or early 2000s, it was only the mobile phones that were using this lithium batteries. But in 1997, Nissan Altra has first released its electric vehicle with lithium based batteries. There started the evolution, or there started the uh, revolution in the market with lithium batteries. So this is what is the timeline of battery development from 1750 to 2020. So in 1799, sorry, 1780, Galvani found electricity from frog. Then 1799, Volta invented the voltaic pile. 1812, there was another pile, and so on. The battery size, these are all cells. Cell is nothing but a battery. In 1836, you see the size of a battery. It is called Daniel cell. Then 1859, lead acid battery. So that was a very big size lead acid battery. And you see lead acid batteries often in our homes when we purchase UPS and inverter. In 1866, this Leclanche cells were introduced. 1886, it was first patented, and then 1899, so on, and then 91, commercial lithium ion battery by Sony. And for this inventions in the battery, 2019 Nobel Prize was given for Professor John B. Goodenough, Professor M. Stanley Whittingham, and Professor Akira Yoshino. And in 1980, if you see, there is something called nickel metal hydride batteries. During that time, it was not very popular, but now again they are gaining nickel metal hydride batteries are gaining its popularity in the recent times. So why are we actually shifting from lead acid to lithium ion cells? So it is because, as I told, it is higher voltage cells, which is around 3 to 3.6 volts, whereas nickel cadmium cells are only of around 1.2 volts. Higher energy density, around 250 watt hour per kg, which means if you have 1 kg of battery, it can store around 0.25 units of electrical energy. 250 watt hour of electrical energy. No memory effect, so there is no nothing like storing or other effects. Again, lighter, smaller, and long lasting. So these are some advantages why we are actually shifting to lithium ion. So the EV battery pack, what we consider, it is having around 200 to 250 watt per kg. And lead acid battery, whatever you have 40 watt per kg, it is almost 5 times of the energy density is 5 times more when compared to a normal or conventional lead acid battery. So this is the structure of a lithium ion battery. So you have one anode and a cathode with a separator in between. So these are the positive terminal and below is the negative terminal. The outer one is the metal case. So here the cathode which is used for lithium ion batteries is lithium metal oxide. It may be LiCoO2 or LiFePO4, LiNiMnCoO2. And the anode is graphite. And the electrolyte used is LiPF6, which is a carbonate solvent. And the separator generally we use is a polyethylene or a polypropylene membrane. And collectors are anode and cathode, which are on the top and bottom. So this is how it looks like when you see it in a cylindrical one. And you also have another kind of lithium salts, which is called prismatic. That is what you use in our batteries and mobiles and laptop charger, laptops. So this is the kind of a prismatic cell lithium ion, where you have one metal case. Inside you have an anode separator and a cathode. So this is how the same thing. This is how it looks like when you have this. Sorry, yeah, when you have this other the same cylindrical structure. So this is how everything happens. Now you might have seen not currently, but in some 5 years to 10 years back, you might have observed some batteries used to bulge because of some unknown reasons. It used to bulge the lithium ion batteries. So that is a false or a failed cell. And if it is a good cell, there will be no bulging and all. And then we have uh, this. These are all actually the pouch celled lithium ion batteries where we have an negative electrode, positive electrode, again separator, and we have one pouch. They are all put inside one pouch. So this is what is the working of a lithium ion battery. So during charging, lithium ions will move from cathode to anode through the electrolyte, and the electrons will move through the external circuit. So here we have this anode and cathode and anode terminals. So when charging, it will move from cathode to anode, and the electrons, whatever is there, they will move from the external circuit, that is this light or whatever you connect here, an electrical load. So electrons will flow through this, that is the current will pass through this. And whereas during discharging, it is the opposite. So here you have a reverse flow of this electrons. So generally, when, as I told, this electrolytes, the anode, cathode, and all, they are Li. At the cathode, you have LiCoO2, which is given or which is decarbonized or demoleculed as Li1 minus X CoO2 plus lithium ion plus extra electrode. And at the anode, you have C plus XLi plus and Xe minus, which is resulting in LiXC. So overall reaction, you will get some lithium ions, which will be floating from anode to cathode and vice versa. Coming to the characteristics of a cell, The cell characteristics, nominal voltage is 3.6 to 3.7 volts. Energy density is around 150 to 250 watt hour per kg. And another advantage of this lithium ion batteries is its life cycle. So the life cycle of a lithium ion battery is around 1000 to 3000 cycles, which is very high when compared to lead acid batteries. And the efficiency of this lithium ion batteries are also very high, which is approximately 90 to 95%. So 90 to 95% efficiency of a lithium ion battery itself tells that whatever the energy it is getting charged, it is almost able to deliver the complete energy. And actually, this coming to the nominal voltage, what exactly is the nominal voltage is in simple words, I should tell you, like, you have a 3.6 volt battery, for example, that is the nominal voltage. So that is an average voltage of a battery. Now, if you charge your battery completely, that is, you consider the example of your mobile. So we have two important things in a battery parameters. First one is the voltage. Second one is the SOC. SOC is called the state of charge of the battery. The state of charge of the battery is nothing but how much charge is present in the battery. So if the battery charge is 100%, it does not mean that your battery voltage is 3.6 volts. It means your battery voltage is a bit more than 3.6 volts, around 3.8 or 3.9 volts, maybe 3.75 to 3.9 volts. And when your mobile battery, I'm only talking about mobile battery because we see the state of charge. I mean, it is very easy for us to see the state of charge in a mobile battery. So whenever you're using the mobile, the battery is getting discharged, and your mobile battery state of charge is slowly coming down to say around 10% or 20%, or you say 0%. It does not mean your battery voltage is zero. So a lot of people have some misconception here. You see in your mobile, if it is 0 volt, your battery is also 0 volts. No, the battery voltage is not 0 volts. It is called, I mean, it will be around 3.3 to 3.4 volts, 3.3 to 3.4 volts, where or which is called as the cutoff voltage. So beyond this cutoff voltage of 3.4 volts, you should not discharge the battery further. So at this 3.4 volts, automatically all the loads will be disconnected. So your mobile will get automatically switched off after it reaches 0% of state of charge. Similarly, the upper limit, we call it as the maximum charge voltage. So beyond that voltage or maximum voltage, we should not charge your battery. So nominal voltage is 3.6 volt. Maximum voltage is around 3.75 to 3.8 or 3.9 volt. The minimum voltage beyond which it should not discharge is around 3.4, 3.3 to 3.4 volts. So this is what the battery limits are. And if you charge your battery continuously, especially the lithium ion batteries, if you charge continuously, there is a chance that the battery performance may be degraded. That is, the number of life cycles, which is almost 3000 cycles, will come down. So how to use your lithium ion battery? So whether it is your mobile or a laptop or an electric vehicle, to that matter, any lithium ion battery, you should charge it only when it is 20% of the SOC. From 20%, you should start charging, and you should charge it only till 80%. You should not go always to 100%. So 20% to 80% should be your charge discharge phenomena. That is, you should charge at 20%, you should charge it till 80%. Again, when you start using your battery, after 20%, you should not use it further. So this should be your charge discharge cycle. Then the performance of the lithium ion battery will be excellent. And based on this charge discharge cycle, because the cycles, it means from one time complete discharge to 100% or maximum SOC, from there again to the minimum SOC. So if you use this range, your battery will work very good, and it will last for a very longer period, for a very longer period also. So this is what is your characteristics of your cell. And if we compare this again in lithium, we have lithium cobalt oxide, lithium iron phosphate also, and also next generation is lithium nickel cobalt aluminum oxide. So there are different combinations of nickel battery, lithium ion batteries itself, I mean, with lithium ions itself. So if you see here, we have the lithium cobalt oxide, which is LiCOO2 chemistry, lithium ion phosphate, LiFePO4. We call it as LFP batteries. Next is nickel manganese cobalt NMC batteries, and this is one more advanced technology of battery. Lithium nickel cobalt aluminum, we call it as NCA batteries. So almost all the batteries have almost a similar voltage rating of around 3.2 to 3.8 volts. If we clearly observe the milliampere hour capacity per gram, that is to be simple, to keep it in very simple words, 150 mAh of the capacity can be stored in 1 gram. So 1 gram in, to be just an example, to be very simple, that's all. Okay. So every gram, yep. So every gram can hold only 150 mAh of battery, capacity. And the key features of lithium cobalt oxide is they have very high energy and low thermal stability. And they are generally, this is the technology which is generally used in mobile phones and laptops. But since cobalt is present, they are more expensive and they are not used in our EVs. And lithium ion phosphate, they are mainly used in electric vehicles, energy storage in solar applications, and many. Very safe compared to lithium cobalt oxide, and they also have a longer life cycle when compared to lithium cobalt oxide. NMC again, they are also now gaining their popularity in electric vehicle because they have a optimal compromise between the safety, cost, and performance. Last one, which is again coming into the picture nowadays, which is around 200 mAh per gram capacity. This is having a very high energy and high power. So this is what is used by Tesla in their electric vehicles. There is an advantage, like it is having very longer life compared to all, but the problem is with respect to safety. So out of all, lithium ion phosphate are more safer. More safer, I mean to say, because of its high thermal capability, LFP is considered to be more safer. Along with that, it also have a flat discharge curve. So what do you mean by flat discharge curve? It is like it cannot discharge more current at the same time. So it slowly discharges. So that is one advantage for safety concerns. So in a battery, the cathode is actually the source and sink of the lithium ions, which determine the voltage and capacity. And the lithium in all these batteries, it intercalates or de-intercalates. That is, it transfer the charge without actually destroying the structure. and anode stores the lithium during charge, and the reaction is, as we have seen, Li plus E minus plus C6 gives rise to LiC6. And silicon based, the the next generation technologies are the silicon based, which is having a very higher capacity, and the lithium metal, which is ideal for solid state. And electrolyte, it actually provides the transportation of Li plus, which is not electrical conduction, it just helps in movement of the lithium ions. SEI, that is the solid electrolyte interface, it forms on the anode and it helps in preventing from decomposition, and it is essential for improving the lifetime of the battery. And we have one separator. So the separator is generally very thin, around 20 to 25 micrometers of porous polymer. It is used for preventing the short circuit and allows the, used in this transport of the lithium ions. And it also has a safety measure. It is also used for safety purpose, wherein it melts if there is some block current. It melts to block current if there is a overheating. So these are all again lithium-based batteries with their energy densities and their applications. So lithium ion, lithium polymer, LFP, lithium sulfur, and lithium air batteries. So lithium air is not commercially available, but it is still research is still going on. It is because the energy density is very high, 1000 watt-hour per kg. It will be an added advantage and makes all your batteries even lighter than what they are now. These LFP batteries, they are phosphate based and are more thermally stable and have a very lighter, slightly lower voltage range, around 3.2 volts. And compared to lithium ion, which is 1000 to 3000 cycles life cycle, it is 3000 to 5000 cycles. And it is almost used in all electric vehicles. Most of the electric vehicles prefer LFP. Next, lithium polymer batteries, where we use gel or the solid electrolyte. It also has a very good higher energy density, and used in drones. So the advantages of these lithium technologies is like it has a very high voltage, high specific density, long life cycle, fast charging. And coming to this fast charging, one important point is like compared to lead acid batteries, we have more charge and discharge rate in your lithium ion batteries. One disadvantage of this lithium ion batteries also is there. Most important disadvantage, like you need to have someone or something to control the current, charge current and the discharge current. Like in case of a lead acid battery, you simply connect the charging circuit, it keeps on taking the required amount of current. Whereas in case of lithium ion batteries, if you make it into a battery pack, we generally use something called as BMS, battery management system. So that the main functions of the battery management system is to always ensure that the battery current is in safer limits, that is within the prescribed limits of the battery pack for which it is designed for. Along with that, it also should ensure the battery's state of charge. It also should ensure the thermal limits. The thermal limits, I mean to say, the maximum temperature what the battery can withstand. So the battery, generally inside a battery, we have a battery management system with one thermal sensor current sensor and voltage sensor, which senses the current continuously. What is the amount of current that is flowing into the battery? What is the current amount of current that is coming out of the battery? What is the total voltage of the battery pack? Along with the what is the temperature of the battery pack? So these are all very important in especially lithium ion based batteries, whether it may be LFP, it may be lithium cobalt, or whatever it is. So this battery management system is very important after you design your battery pack, and that is the one which maintains your battery in a safer limit, ensuring your safer ride. So in mostly in the last 1.5 year, every one of us every one of us have heard about electric vehicle blasts or catching fire. Some randomly they catch fire. Uh, by with God's grace, nothing happened to people who are riding the vehicle, but most of the cases it was with when the vehicle was parked. So the reason why it it caught fire is like because of failure in the battery management system. That is what the total survey, I mean, the total investigation report was all about. Why it failed? The first reason, like it might be because of the failure in the battery management system. So the battery management system was not that efficient to give the proper indication to the driver or the person who is riding to tell that the battery has crossed its temperature limit. You please cool down the battery. That was not clearly indicated to the user. That was the main reason this happened. And if you see, all these incidents happened only during summer, not during any other season. It is because in summer, automatically the temperature of outside atmospheric temperature is high. Along with the atmospheric temperature, when you ride your vehicle, there will be some temperature also inside the battery. Like when the current is charging or it is discharging, there will be high temperature inside the vehicle battery. So the battery should be provided with a proper cooling technology also, especially for lithium ion batteries. Even though these are some complexities and challenges that occur in the battery, we still go with lithium ion based batteries for the only advantage like fast charging and long cycle life, and also they have very less self discharge. Now, why? What do you mean by self discharge? It is like when you keep a battery unused. When you keep a battery unused, the charge in the battery will be automatically or reduced after some time. So that, uh, like if you see a lead acid battery, even though you use the battery or don't use the battery charge will slowly reduce after certain time. So even if it is unused, why should it get reduced? So that is what you call self-discharge. And that self-discharge for lithium-based battery is very low. Another advantage is temperature. So these batteries have a very high or wide temperature range. So from minus 20 degrees centigrade to even 70-75 degrees centigrade, these lithium ion based batteries can withstand. So it has been the first, as I was telling you, when it can withstand, it should be communicated like it is more. The battery temperature is high. So you please shut down your vehicle. Some communication should be given. So that is where the failure is, even though it has a very high temperature range. The disadvantages is in terms of safety, what you call thermal runaway. That is what if it is if it is having more temperature, it should automatically be turned off and completely be shut down. Cost is a bit expensive. So if you consider a vehicle, any vehicle, two-wheeler vehicle you consider, around 60% of the vehicle, 60 to 70% of the vehicle is only for the battery. So if you buy a vehicle for say 1 lakh or 1.2 lakh, 75 to 80,000 is the battery cost. So that is where the cost of the battery. Now it has come to that, but previously it was even more. Next is lithium reserves are very limited. As I told, recently India has also found some lithium reserves in, I think, Jammu Kashmir. And another important thing is recycling. So recycling, what exactly this recycling means is, hardly we give what you call the life cycle. Now, if you go to any electric vehicle shop and ask for the warranty, so what they do, they tell generally it is around 5-year warranty. And if you are maintaining the vehicle charge discharge cycle in a very proper way, it may last up to 8 to 9 years. But after 8 to 9 years, what will you do? So after 8 to 9 years, still the battery can survive, but it is not fit for electric vehicles. So when it is not fit for electric vehicles, we need to check for some other alternative application of that used battery. So it is used in the so-called renewable energy applications. After 15 years, I mean, after 5 years or 6 years from then, again after 15 years, the battery is now unused. How to dispose the battery? How to dispose the battery? That is one more important point or important uh, research program or research uh, gap where people are still doing research. Some companies have come up with some commercial solutions, but even then, when they remove the battery, there are some toxic substances which is causing some side effects to the human beings who are to the workers who are working on that. So this is one, and another one is the environmental issue. When you take these brines, when you extract lithium from the brines, they are causing water depletion. So there are few disadvantages also with that. So how actually this lithium ion batteries are being manufactured? So first they are mixed with all, then coated, dried, then you go with solvent recovery, stack, clander, stacking, then finally you weld it and then you sell it. So this is what is your complete what you call lithium ion battery manufacturing process. I think this has already been, yeah, this has already been covered. So these are all some other the same. So this slide is only to tell you the importance of lithium ion when compared to other. So if you see, lithium ion has a very high energy density, very high life cycles, 2000 plus life cycles. And when compared to dismantling the lead acid batteries, these lithium ion batteries have less toxicity, but the toxic elements are still present. And it is now, used in almost every this one. And as I told, the major drawback or major challenge is designing its battery management system. So it requires a very sophisticated battery management system. So these are the lithium ion batteries that are available for recycling worldwide. So in 2019, the total number of the batteries that are available is around less than 2 lakh. Now in 2025, if you see, or it is around 8 lakh, approximately 7.5 lakh. Even if you proceed further, by 2030, the batteries will reach around 14 lakh or 12 lakh plus, and you need actually to recycle all the batteries. There comes the difficult task. So India, not only India, the countries, all the countries should know how to recycle the batteries. I'll Even though I'm an electrical engineer who is working on electric vehicle using the batteries and all, off the records, I'll tell you, like, I'm not completely in favor of electric vehicles. The reason why I tell you is maybe in 1990s or later, we used look. For example, you go to buy some fruits or something. You used to carry some bag, but there they started this evolution of polythene bags. So they used to give polythene bags. You are now not at all carrying any, those days you did not carry any bag. You simply go get that polythene bag completed. Now what people are telling is stop polythene. Don't use polythene bags. They are they are not good for environment. So now the polythenes are not able to go into they are not really solvable with the earth, and they are creating a lot of issues, environmental issues. And that is what may happen for the lithium-ion batteries and the electric vehicles also. Lithium-ion batteries used in the electric vehicles also, maybe by 2040 or so. So it is better to have a very good plan on how to recycle them in a environment-friendly way. So these are all various applications of lithium-ion batteries. So now you see how many applications we have, and are we really having some alternative solutions? These are all some research problems where you can work on. If you're whatever the field you belong to, whatever the branch you belong to, this is a common research problem to all. Mechanical people can try in how to make or disassemble all the lithium, the battery the battery pack in a more environment friendly way. Maybe chemical and chemistry people, they can think on how to recycle them. And other departments, you can take your own research problem on a single area called how to disassemble and make lithium useful again. So, sorry. So there are some case studies also. Tesla battery, it has invented. Then recently, if you have seen Samsung, uh, in some airlines, they have completely banned Samsung mobiles. You don't carry Samsung mobiles. If you have Samsung mobile, you should not enter the vehicle. You should not enter the aeroplane. So there are something that happened with Samsung Note 7. They have some explosions happened inside that. So these are other challenges what we have with respect to this. So what there are like water pollution, air pollution, land pollution, radioactive pollution, whatnot. All kinds of will come when you have no proper idea or no proper policy or guidelines on how to use the battery till its maximum performance. Like you should use the battery till 15 years or 20 years, whatever maximum it is possible, how to use it. Then after using, how to recycle it or dispose it. So e-waste is now dumped. So you may need to have some other alternatives also to check with all these things. So recent advancements and future trends. So there are some recent advancements is with solid state batteries and lithium sulfur batteries, which are having a very high capacity of 1675 milliampere hour per gram and low cost. But the challenge in that is dissolution of polysulfates, which are having a very quick degradation, where the quick degradation happens. So these are all certain aspects where we are there is still some research going on. Sodium ion, aluminum ion, lithium air batteries, how to recycle the batteries, what you sorry, what do you mean by second life battery? Second life battery, as I told you, when you have a very good, when you are starting with a battery, you use it in electric vehicle. The new battery will be used in electric vehicle. After the vehicle, you do some cell balancing things and keep it in renewable energy for storage system, where your charge discharge cycle is not too rapid. It is not too fast. It slowly charges, slowly discharges. So there you can use it for some another 5 to 6 years. So that using the battery for the second time, we call it as second life battery. How to recycle this, how to extract, how to go with some alternative chemistries to improve, I mean, to improve the performance and to make it cheaper and to make it more environment friendly. So these are all how the trend. I think it is already time. Okay. So these are all the trend how people are doing their research in what you call lithium based batteries. The market of the lithium. Yeah, this is the lithium ion battery which could reach 99,300 gigawatt hour by the end of 2030. So this clearly replicates how EV is fast, EV is actually growing in the market. The government itself is promoting EVs. Government itself has promoted polythene covers those days, but now it is telling don't use polythene. Same now EV is being widely promoted by all the government agencies, even not only in India, everywhere. Because of some other, there are advantages. I don't say no, but the demand is too high. Now the demand will be even more high. So this is how it is showing 99,300 gigawatt hours by 2030, not a small amount. So this is what is all about this. So thank you for your patience learning, and that too at late night. So if you have anything to discuss, it is now open for you to discuss.
Thank you so much, sir. Dear participant, it's your turn to may raise your questions and queries. You can also use the chat box for asking questions. Sorry for the technical issues that happened in the last feedback section. And also we are sharing the feedback section of 6 in the chat box, so you can kindly fill it.
Any queries or any discussions? Like, if you have some other points, like say it is all the process of learning. So if you have some other things which you can share it so that it will be useful for me also. We'll also learn together. So any discussions on that aspect also are welcome. If graphite is replaced with silicon, how will it affect the performance? So that is what I'm telling. The research is still going on in that aspect, and sorry, I'm not working in that chemical areas of a battery, so I cannot answer your query. Sorry for that, but yes, research is still going on in that aspect. Maybe if you are from, I'm not sure in which domain you are from. If you are from that chemical or chemistry domain, it is very good. If lithium-ion battery charges extremely fast, what challenges may arise in terms of stability? Yeah, thank you for that. So now the major issue when the battery charges very fast is, as I told you, there are some charge discharge cycles. The charging is very fast, discharging is also fast. So the number of charge discharge cycles, to be more clear, the overall performance of the battery will get degraded. In other words, I'll put it very simple. Now, if you are going with normal charging and discharging of the battery lasts for say 5 years. When you fast the charging process and discharge the process, the battery may not last for 5 years. The battery may last only for 3 years. So again, after 3 years, you need to go with a newer battery or do some cell balancing in the battery. So the performance of the battery will get completely degraded. And even though, yeah, it is good for good for the user at the time of using the vehicle, I mean using the battery, but later it needs to be the performance, the stability, whatever you call, everything will be degraded. And another aspect also is there, if when you are charging the battery very fastly, it means you are giving more current. So thermal stability will completely collapse. So normal battery, when it is charging, say it is charging at somewhere around 35 to 40 degrees centigrade. When you are charging it with fast chargers, actually around some 100 to 150 amperes of current will flow. During that time, you just think how much amount of heat will be dissipated when 100 amperes of current is flowing. So thermal stability will be highly affected during that time. Hope I answered it. Thank you.
I hope it's over. On behalf of the organizing committee and all the participants of FDP, I extend my sincere gratitude of our distinguished resource person, Dr. Hemachandra, for your enriched and outstanding talk. If I like to welcome Ms. Anju for giving a thank you note.
It's my privilege to extend a heartfelt note to thanks to our esteemed resource person, Dr. A. Hemachandran, for delivering an exceptionally informative and insightful session on the role of lithium-ion battery technology. Your presentation provided a clear understanding of how lithium-ion batteries have transformed modern energy storage, home, consumer electronics to electric mobility and renewable energy interaction. Your expertise helped us appreciate not only the working principle of lithium-ion system, but also their advantages, challenges, and future potential in shaping a sustainable and energy efficient world. On behalf of all participants and the organizing committee, I express our sincere gratitude for your valuable time, effort, and willingness to share your expertise with us. We are grateful for the learning experience and look forward to future interaction. Thank you very much, sir.
Yeah, Sir Dr. Sudhanshu Chakraborty, sir, I'm sharing my mail ID in the chat box itself. I'd like to thank the organizers, especially Dr. Praveen Rose, sir, for giving me this opportunity, providing me this opportunity. And I think I should thank all the participants for spending their time late night. So, great. So, congratulations for your time and effort during late nights. And thank you for the organizers. Thank you. So, I'll share the PPT with the organizers. They can circulate it to you. Many men are asking for PPT. So, sir, please, ma'am, please take care of that. I'll circulate it. I'll give it to Praveen Rose, sir.
Okay, sir. Thank you so much.
Yeah, thank you.
Dear participant, please complete the feedback form each section, which will you find posted in the chat box. Your input is invaluable. We look forward to seeing you all the sharp time tomorrow for the section 7. Thank you, brilliant participant, for another fantastic day of learning. We are now more than halfway through this FTP and the momentum is incredible. Keep that energy high. See you tomorrow. Have a wonderful rest of day. Thank you.